4.6, numerical integration. Area of a trapezoid is 1/2 times the height times base 1 plus base 2. So this is very similar to LRAM and RRAM and MRAM, only that instead of using rectangles, right, because the R stands for rectangular approximation, we're using trapezoids. And the purpose of using a trapezoid is that when you have a whole bunch, like right here, trapezoids piled up together, they tend to become more of a curve, right? Whereas a whole bunch of rectangles, wow, that's an awful picture, but a whole bunch of rectangles would leave a lot of space unaccounted for if I did have a curve, right? But the trapezoids altogether, I mean, they pretty much cover the space. So again, the formula for a trapezoid is 1/2 times the height. So this is supposed to be the height. And then these are my bases. It doesn't really matter which one's 1 and which one's 2. Well, on the coordinate plane, when we graph these said trapezoids, the height is always going to be the x value. So that's going to be our height. And then the y values on the left and on the right, those are going to be our bases. Okay? So, example 1. Use 4 trapezoids to approximate the area under the curve y equals x squared minus 2x plus 2 from x equals 1 to x equals 3. We're only looking from here to here. I can make straight lines, that would be fantastic. Now 4 trapezoids would mean that I'm going to have to cut this up in the middle. So we have 1, we have 3, we have 2, then we also have 1.5 and 2.5. So our trapezoid is going to look something like this. Let's pretend I can draw straight lines, please. So it's 1/2 times the height. Now the height, as mentioned before, is the x value. Well, all of these trapezoids have the same height because they are even widths. So 1/2 times the height, which is another half, and then times base 1 plus base 2. So it would be a lot easier if we just took all the base 1s and base 2s and added them together and then multiplied times the 1/2 and then the width, which is the height, which in this case happens to be 1/2 or 0.5 or whatever. But I do need all of the heights. I need all of my y values. So I need this y value, right? Because that'll be my base 1 for that trapezoid. But then I also need, let's do that in purple, no green. I also need this height because that'll be my base 2 for that very trapezoid. But then, if you pay attention, for the next trapezoid, I still need this height because that's my base 1 for that trapezoid. So I'm using this value, this y value, twice. And then it actually repeats, or this, what's the word? Pattern repeats. Because see, now this is my base 1 for this trapezoid here. And then this is my base 2 for that same trapezoid, but it's also my base 1 for the following trapezoid. And then my base 2 for this said trapezoid happens to also be the same as base 1 for the next trapezoid. But then, let's see, what color have I not used? This base right here doesn't get repeated because it's just the base for this one trapezoid. Just like the very first one, right here, was just the base for this trapezoid. So, my point is that these bases, the three in the middle, the interior ones, they're always going to repeat. Okay, I'm going to find these values real quick. So I found the values. I plugged in 1, 1.5, 2, 2.5, and 3, and I got my y values. So again, formula is 1/2 times the height, which is basically the width of our trapezoids here, times base 1 plus base 2. And I was trying to explain how the bases repeat because my base 1 for this triangle doesn't repeat, but the base 2 is the same as the base 1 for the very next trapezoid. Did I say triangle earlier? Wait. So, in doing base 1 plus base 2, base 1 plus 2, I'd be doing 1 plus 1.25. Right, that would be my first one. And of course, I don't have space, so I'm going to have to do this on the next line. And then I would add the base 1 and base 2 for the next triangle, or what is this called? Trapezoid. So that would be, this is my base 1 and this is my base 2. So 1.25 plus 2. And then I would add the next 2, which would be now the 2 and the 3.25. 2 plus 3.25. And then I would add, and then I would add, why is this not working? There we go. And then I would add the base 1 and base 2 for the next trapezoid, which would repeat 3.25, but then I would use the 5 as well. I think I can fit it? Barely. Okay, so anyway, the reason I'm going over again the fact that the bases repeat is because there's an easier way to write this. And I'm going to just rewrite it down here. The 1/2 times the 1/2, that still exists, right? But then, basically, paying attention to these numbers here, I'm going to be like 1 plus 2 times 1.25, because it repeats, right? Repeated here and here. That's 2. Plus 2 times 2, because also there's a 2 and there's a 2. Plus 2 times 3.25, because here's 1 and here's 1. And then finally, that's supposed to be a plus. Looks horrible. Let me erase that. Plus the last number, which is 5. Okay? That way, you take care of how the ones in the middle are doubling. Right? We use them twice. But anyway, here's trapezoidal approximation. I have 1/4, and then let me add all this up. So in adding all of this, I got 19. So I have 1/4 times 19, which is basically 19 over 4. And voila, there's my approximation. No decimal required. You could, but you don't need it. That's the beauty of calculus. But either way, it would be 4.75. Okay, example 2, the trapezoidal approximation of the integral from 0 to pi of sine x dx using 4 equal subdivisions on the interval of integration is. So let me sketch this out real quick. I think that's the best my picture is going to get. Okay, so we're using trapezoids from 0 to pi. There's 4 of them. I divided this up evenly. So it's going to look something like this. And then there, and then there's another trapezoid, and then here's another one, and here's another one. So this is when, of course, knowledge of the unit circle comes in handy, because you should be able to figure out these values without a calculator. For example, sine of 0 is 0, but then, the sine of pi over 4, let me write that down, 0, the sine of pi over 4 is square root of 2 over 2, but then the sine of pi over 2 is 1, and then the sine of 3 pi over 4 is also square root of 2 over 2, and then the sine of pi is 0 again. So now my trapezoidal approximation is going to be 1/2 times the widths, right? So each one of these has a width of pi over 4, because basically I took pi, divided it up into 4 pieces. So it's a fourth, a fourth, a fourth, a fourth. So pi over 4. And then I get to be like, okay, so my first base is 0, which obviously I don't have to write, but I'll do it anyway. Plus the square root of 2 over 2, but remember, these on the inside are going to repeat. They're going to be doubled. So 2 times the square root of 2 over 2, plus 2 times 1, which is 2, plus 2 times the square root of 2 over 2 again. And then the last one is just used once, even though it's 0, so it's not of any consequence. Then I have pi over 8. And then if I look at this here, I have 2 square root of 2 over 2 plus 2 more square roots of 2 over 2 for a total of 4 square roots of 2 over 2. I change that to blue. Plus 4 square roots of 2 over 2. And then plus 2, right? Didn't forget about him. All right, so let's see. Ooh, look, the 4 and the 2 just becomes one big fat 2. Let me go down here. So I have pi over 8 plus 2 square root of 2 plus 2. Oh, you know what? I just realized something. Totally made my parentheses disappear. My bad. Okay, so back on it. Now this would be a good answer. If I look at the multiple choice answers, none of them look like this, which means they probably simplified something. I see that there aren't any 2 square roots of 2, and that's probably because this 2 and that 2 can be factored out. So now I have pi over 8 times 2, because I'm factoring out these 2's. Factoring them out leaves behind a square root of 2 plus a 1. And then that's probably why I get this. It's one of those. But then the 2 and the 8 cancel out. Or well, not cancel out, but they can be reduced. And I end up with pi over 4 square root of 2 plus 1, which is this one. Only that they wrote the 1 first. Big deal. Okay. Next. Example 3, suppose the table below shows the velocity of a model train engine moving along a track for 10 seconds. Using a trapezoidal approximation with 10 subintervals, estimate the distance traveled by the engine in the first 10 seconds. So finding the area underneath this curve that we can't see anyway, right? That is the distance traveled, or an estimate anyway. So 10 subintervals, so this is already spaced out into 10 spaces anyway. So like these 4 are going to give me my first trapezoid, right? Just like these last ones are going to give me my last trapezoid. And then in the middle, it's going to be those 4. They share, right? And the next one is going to be these four. Oh, look, I get shared again, right? And you just keep going. I'm going to have 10 of these. I'm going to get rid of this stuff. Let's see. So trap. So 1/2 times the width. Now, the widths, all of these are evenly spaced out by a second. So I could write 1 if I wanted to. Times. And here we go. So the first base is 0 plus 2 times the next base. Again, remember, I'm going to highlight it. These numbers all get doubled. They get used twice. Not the first and not the last. Luckily, in this case, the first and the last is 0, so they have no consequence anyway. But of course, that won't always be the case. So 0 plus 2 times 12, which is 24, plus, let's see, 2 times 22, which is 44, plus 2 times 10, which is 20, etc., right? I'm getting these numbers because I'm multiplying these all by 2. And so I'm just going to keep going. So here we go. 0 plus 24 plus 44 plus 20 plus 10 plus 26 plus 22 plus 12 plus 4 plus another 12 plus the last 0. And all of these highlighted numbers, I just made sure that I doubled all of them except for the 0 on top and 0 on the bottom. Not that you could possibly double that anyway. So then we have 1/2 times all of this, whatever that is. So I got 174, and then half of that is 87. So that's the distance traveled by the model train, was it? 87 inches. Example 4, the function f is continuous on the closed interval from 1 to 7 and has values that are given in the table above. Using the subintervals 1, 4, 4, 6, 6, 7, what is a trapezoidal approximation? So they're giving me the intervals to use. So from 1 to 4, these are going to give me my first trapezoid. So trap 1/2. Now, if you notice, from 1 to 4, right, my width would be 3. From 4 to 6, my width would be 2. And from 6 to 7, my width is 1. So I'm not going to do this the same way I did the previous examples. I'm literally going to have to multiply a width every time I do a trapezoid. Every time I do a trapezoid with the base in 1 plus base 2. So the first trapezoid has a width of 3, and then base 1 could be 10, and then I'll call the second one base 2. So that's my first trapezoid. That's this right here. Now the next one would be these two. So I'm adding. Now my width here is 2. And base 1 will just be 30, and then 40 will be base 2. And then the next and last trapezoid has a width of 1. I don't have to write that, right? And then base 1 will be 40, and then base 2 will be the 20. And then that's it. Let me erase this. Okay, so this is a classic AP question. I had to do trapezoidal, but they gave me the subintervals, and of course they don't have all the same widths. The 1/2, of course, is a part of the formula that doesn't change no matter what. And then just solve. And there you have it. Did the math, I got 160. Example 5, using 8 equal subdivisions of the interval from 2 to 12, the RRAM approximation of the integral from 2 to 12 of f of x dx is 16.6. So RRAM is 16.6. And the trapezoidal approximation is 16.4. What is the RRAM approximation? So at this point, it would be important to point out that whenever you do a trapezoidal approximation, it is equal to the average of LRAM and RRAM. So if I take LRAM and I add it to RRAM and divide by 2, because that's how many numbers I'm adding, right? So this is the average. It is equal to the trapezoidal approximation. So the trapezoidal approximation is 16.4. So 16.4 equals, now the LRAM is 16.6. So 16.6, and RRAM is what we're looking for, and then divide by 2. Here, basically, I have an equation. Your job is to solve for RRAM. First step I would do is multiply both sides by 2. Okay, that gets rid of that. So I have 32.8 equals 16.6 plus RRAM. And then, of course, subtract. And we get RRAM by itself. And then 16.6 leaves me with 16.2. And that would be RRAM. You could easily check and be like, ooh, 16.6. That's 16.2 divided by 2. What's that give me? So I've got 32.8 divided by 2, which is 16.4. And yes, that is what I started off with, right? For trapezoid. Okay, that is it.